Okay, we can finally talk about blockchains. I'm sure you've heard this term before. As you might have noticed already, technically a Bitcoin doesn't really exist. To find out how many Bitcoins someone has, you just look at the total number of Bitcoins he received and the total number he sent out. And the difference is his current balance. So to have any Bitcoin, someone must have received it first from a transaction. If you remember what we said in the last chapter, a person solving the hash puzzle will receive a Bitcoin reward. This is actually also just a transaction, but a special one, where the sender is no one. So the Bitcoins are created out of nothing. And so you can see here, Charlie found 2 solutions for the puzzle through mining and received in total 100 new Bitcoins. And then he sent 80 of those Bitcoins to Bob. So now everyone sends out these transactions to the network, but how are we organizing them? Because remember, we need to find consensus on the history for all transactions. So finally, after all that time, we can talk about blockchains. This is how the transactions are organized. And a block is a collection of transactions combined with the solution for the cryptographic hash puzzle for mining. So each block is connected to one solution to the puzzle. So it will always have at a minimum one transaction like this that's creating the new Bitcoins for mining. The miners continuously look for new solutions, and once found, they can publish a new block and include as many new transactions as possible. Within one block, a miner can basically freely choose the order of transactions. But the security comes from him, of course, not being able to publish every single block. So now you end up with this constant stream of transactions which are shared over the whole network and are continuously put into new blocks. Each new block will reference the previous block. But because we are operating in a distributed network, sometimes this can lead to problems. Imagine this is our distributed Bitcoin network. All of these computers here are miners, so looking for the next solution of the cryptographic puzzle. They are all connected with each other, either directly or indirectly, and all information between them is shared. So you can see here, they all currently have the same 1252 blocks stored. Meaning currently they have full consensus and everyone agrees on the same transaction history. And now imagine 2 miners finding a solution at the exact same time. One miner is over here and the other one is over here in the network. They both publish their solution to the network at the same time. And now these miners here will see the solution from this miner first. And they will try to find a new solution on top, which is based on this yellow solution. But these miners here will see the solution from that miner first. And they will try to find a new solution on top, which is based on that purple solution. So now we have a disagreement between participants in the network. And those 2 different solutions will not only be a different solution, very likely they also included differing transactions. So we really need to resolve this disagreement. Such disagreements are called forks. And they can actually go over even multiple blocks. Because imagine now here on the left, someone finds a new solution at the exact same time as someone here on the right also finds a new one. Not very likely, but theoretically possible. And you can see that theoretically this could continue for all eternity. This would be catastrophic. Now we have no consensus over the network at all. Luckily, it's all about probabilities. The longest chain always wins. And eventually one fork will win. And you can calculate how likely these long forks happen and just wait long enough to have a probabilistic guarantee it won't change again. When 2 chains are identical, miners can choose either. Most probably they will choose the one they saw first. But if they choose the wrong one, so to speak, meaning someone finds a solution on the chain they were not working on, they simply abandon their past chain and work on the new one. So theoretically, not practically, someone could come up with a Bitcoin blockchain from the first block where everything is different to the current Bitcoin blockchain as we know it, and which is also longer than our current blockchain. And then the rule is the longest chain wins. So all Bitcoin transactions ever created would be reverted. But of course, this will never happen because practically no one would be able to get such a longer chain. For a user, this means to have effectively 100% guarantee that a transaction is actually confirmed and not reverted, you have to wait a few blocks. How many exactly? Well, it's hard to put an exact number on it because it's all about probabilities. But to give you some reference, most exchanges accept deposits already after 3 block confirmations, and certainly after 5 confirmations, you have a very, very high probability to have the transaction stay in the current blockchain. 1 block in Bitcoin takes about 10 minutes. How can that be if new blocks are found whenever a new puzzle is solved? Wouldn't that mean if more people try to solve the puzzle, it would speed up when new blocks are found? That's because Bitcoin automatically adjusts the difficulty of future puzzles based on how fast prior puzzles were solved. Miners are finding solutions in just 5 minutes on average. The difficulty will be increased. Miners are finding solution in 15 minutes on average. The difficulty will be decreased. And if you think back to what the puzzle was, difficulty here just means the number of zeros required in the beginning. And now, all of that, my friends, is the core idea behind blockchains. An immutable, distributed history of transactions secured by miners.